Section 18.2 talks about entropy changes, both chemical and physical. Moving on to the third law of thermodynamics. So now we can predict the sign of our entropy based on the guidelines from 18.1, but now we can actually calculate our entropy using the third law. So the third law of thermodynamics states that entropy of a pure, perfectly ordered crystalline substance at absolute zero gives an entropy of 0. So essentially, everything we're dealing with does not have an entropy of 0. It's going to have either a negative or a positive, because the only thing that will have an entropy of 0 is something perfectly ordered, crystalline, and at absolute 0. So how do we start calculating our entropy? So entropy values are based on the third law, and their units are the standard molar entropy, and that's joules per mole Kelvin. Where the standard conditions are temperature is 298 kelvins, that's room temperature, 1 atmosphere gas, and then the concentration is 1 molar. And we can calculate changes in entropy using this equation, which I know looks a little complicated, but I promise it's really simple. So we can calculate our entropy of the overall reaction by taking the sum of our products. So we calculate the entropy of each product, add them together, and then subtract it from the sum of our reactants, where that M and the N out front just means the stoichiometry out front. So M and N specifically are the coefficients of the products and reactants from the balanced chemical equation. So even though this looks a little complicated, I'm going to show you how simple it really is. So majority of everything has an entropy, and it's already been calculated and it's given to us in a chart. So here's just an example where they give us a gigantic chart full of entropies, and they're asking, if they give you a reaction, can you just calculate the overall entropy of the reaction? Well, luckily, yeah, they just give us numbers. We just have to set up the equation and then plug and chug. Here's an example of that. 18.3, so predict the sign of delta S, so we got to figure out if it's a plus or minus, and then calculate the standard entropy change associated with the reaction of gaseous hydrogen and gaseous oxygen to form water vapor. So in order to calculate these problems, I need to know what the reaction is, and I need to know what the entropies are for each individual reactant so I can set up the equation. So I shifted everything around so I can make more room. Our products are going to be water, and our reactants are going to be H2 and O2 gas. And so now I'm going to plug in the values for this equation. So my delta S, not of my reaction, is going to be my sum of the products. And since I only have one product, I don't really need to take a sum because there's only one of it. So I'm going to put everything in the products in a bracket. But remember that it's important that the coefficients out front need to be included. So I need to have a 2 out front, and then I need to multiply it by the delta S of H2O. And since I only have one product, I don't have to find a sum, it's just that number. And then you subtract it by the sum of the reactants. So we have H2, and there's a 2 out front, so it's going to be 2 times the delta S of H2, and then the sum means I have to add all of the reactant entropies up. There's a 1 out front of O2, so we're not including that, so it's just going to be the delta S of O2. So this is why it's really important for you to set this up, because once you have this set up, all you have to do is plug in those numbers. So that's just going to be 2 times 188.8 minus 2 times 130.7 plus 205.2. So that's just going to be the hardest part, is setting this equation up, and then you just have to plug and chug. So our entropy of the reaction equals negative 89 joules per mole Kelvin. I didn't include units in here because technically they're all going to have the same unit in the end anyway. Well, we didn't, normally we predict these values firsthand, but I forgot to put that in the very beginning. But first, let's just predict real quick. It says predict the sign of delta S. We just proved that it was a negative value, but let's look here. We're going from 2 plus 1, that's going to be 3 moles of gas to 2 moles of gas. And so if I'm losing my amount of particles, then that would be why my delta S is negative and not positive. And we use the math to prove that in theory. So I apologize for going a little backwards, but at least it makes sense because we can predict this value looking at the equation, and then we can figure out what is our overall delta S or entropy value. Example 18.4 also says predict the sign of delta S and calculate the change in entropy when 72.85 grams of liquid mercury is vaporized. So first, let's predict the delta S sign. So we're going from a liquid to a gas, meaning that we're going from a semi-orderly structured material into a very disorderly material. So I'm going to predict that the delta S value is going to be positive. Now let's set up our entropy equation. So our delta S of the reaction is going to be the sum of the products minus the reactants. So we only have one product and one reactant, so I don't really need to calculate a sum. So it's just going to be the delta S of Hg gas, since that's our product, minus our delta S of Hg liquid. So mercury is a liquid. So we just have to plug everything in, and since there's no really coefficient besides 1, this is going to be pretty simple. So our delta S of reaction is just going to be equal to 175.0 minus 75.9. So that gives us a delta S of reaction of 99.1 joules per mole Kelvin. So our prediction was correct. We did get a positive increase in entropy, but we're not done there, because technically this question is asking the change in entropy when 72.85 grams of liquid mercury is vaporized. So we're going to have to incorporate those grams somehow, and the way we're going to incorporate them is using the moles here on the bottom part of this equation. So if I'm starting out with 72.85 grams of mercury, we need to figure out a way to incorporate that with our equation, because we're looking for delta S once those grams are accounted for. So if I convert the grams to moles of mercury, I need to use the molecular weight of mercury. And so if I look at the periodic table of elements, I find that the molecular weight is 200.59 grams per moles. So if I'm looking for moles, I need to cancel out the grams. So where is that 200 going to go? So if I want to cancel grams, then I'm going to have the grams on the bottom, because something divided by itself is just going to be itself. So there's not going to be any units there. So I'm going to put the 200.59 on the bottom, and I'm going to have 1 mole on top. So all I did was just invert the molecular weight. So that gives me 0.363 moles of Hg. And I know that I just calculated my delta S of reaction to be 99.1 joules per mole Kelvin. So if I take my delta S of reaction and I multiply it by the amount of moles I just calculated, so let me make this a little bit easier on the units. So I can rewrite that to look like this: joules per mole times Kelvin. And then if I multiply that by 0.363 moles of Hg, I'm going to cancel out those moles, and I'm left with 36.0 joules per Kelvin. So that's going to be my overall answer for this equation, because I had to account for the amount of liquid mercury that they gave us.